Hey everybody, Trey here, and welcome to my 2023 tornado season forecast. In this video, we're going to at least attempt to make a forecast on the distribution and frequency of tornadoes across the U.S. this upcoming spring. Basically, which areas may be favored for tornado production, and whether or not we'll see an above average, near normal, or below average season as far as tornado count goes. As we know, forecasting the frequency and distribution of tornadoes at this range is very, very difficult, nearly impossible. But there are some factors that do tend to modulate the distribution and frequency of tornadoes across the U.S., such as global climate teleconnections, drought, etc. And we'll go and do a deep dive into those in this video, and then formulate some analogs, some past seasons that have similar background conditions that may help us formulate a forecast for tornado activity this upcoming spring. A couple of notes before we get started. As always, I'll be going through and referencing a bunch of different journal articles on these topics. I'll put all of the links to these articles in the description box below so you can do some of your own research on this kind of stuff. And as far as defining what I mean by tornado season and our domain of interest, by tornado season, I'm talking about our typical months where we see increased tornado activity in the U.S., March through June. And then as far as domain goes, we're looking at the places that you typically think of for tornado activity. The Great Plains, the High Plains, the Midwest, the Southeast. We're not talking about the oddball areas like the West Coast or the Pacific Northwest or the Northeast. We're looking at our basic general time frame that we often see increased tornadic activity in the U.S., March through June, in our favored areas for tornado production, the Great Plains, the High Plains, etc. So this is our current count for tornadoes up to this point in the year. This thick red line here is our ongoing tornado count for 2023. This thick black line is our average tornado count throughout the entire year. And you can see, thanks to a very active January, we are well above average right now as we go into the first couple weeks of March. We had, as we said, a very active January and an active period just recently, and so we are well above average. Now, this how we start the year as far as tornado count goes does not really reflect how we finish the year. For example, you can see this solid green line down here is 2020. You can see we started off pretty much the same as we are this year, well above average, stayed that way through about March and April, and then we dipped below the mean and actually finished the year below average as far as tornado count goes. So the correlation between how we start the year and how we finish the year and what our tornado count is throughout the main months of storm season is not really correlated. It is somewhat interesting to note, though, that we did have our most active January since 1999, which ended up being another very active tornado year as a whole. So something to note, although the correlation there is unlikely, it is very weak and unlikely to mean anything in the long term. So the first factor that we can look into is global climate teleconnections, most notably the El Niño Southern Oscillation, or ENSO. And ENSO is driven by sea surface temperature anomalies in the equatorial Pacific, so the departure from the average of sea surface temperatures in the region of the Pacific Ocean that lies right along the equator. Now, as you probably know, we can have multiple phases to ENSO. When we have warmer than normal temperatures in that equatorial Pacific region, we would be under an El Niño phase. An example of which is on this top panel. If we were to draw a line right through the center of the globe, that would be our equator. And we're looking right in here, that region of the Pacific that lies directly along the equator. And you'll see that the sea surface temperature anomalies, you see those reds and orange colors, those are positive sea surface temperature anomalies in that region, meaning that we have warmer than normal water in the equatorial Pacific, and therefore we would be in an El Niño phase. The opposite is true for a La Niña phase, when we have cooler than normal water right along that equatorial Pacific region. And if we have somewhat normal temperatures in that equatorial Pacific region, we would be under what's considered a neutral phase. Now, scientists break this equatorial Pacific region up into a number of different smaller regions to help come up with a number of indices to determine ENSO phase. We have our Niño 1 and 2 region, which is in this green box right here, right off the South American coast. A little bit farther west, we have our Niño 3 region in the purple box here. Even farther west, our Niño 4 region, which is in the orange box. And perhaps the most widely used region within this equatorial Pacific to help determine ENSO phase is this Niño 3.4 region right here. It's in this red dashed box, and it's essentially an overlap of the Niño 3 and 4 regions. And again, it's probably the most widely used metric, the sea surface temperature anomalies within the Niño 3.4 region, to help us determine ENSO phase. As we said, there are a number of different indices used to determine ENSO phase. Perhaps the simplest and most widely used of those is called the Oceanic Niño Index, or ONI. And all the ONI is a 3-month running average of the sea surface temperature anomalies in that Niño 3.4 region. What we mean by 3-month running average is we're taking the average sea surface temperature anomaly in that Niño 3.4 region over a 3-month period. So for example, January, February, March, and then we're using a running average. We're just moving to the next month and then doing the next 3-month period. So that would be February, March, April, May, April, May, June, and so on and so forth. So as we have to remember that climate and these climatic teleconnections are more so looking at trends in these over a longer term period. So that's why we don't take 1 month, for example, in isolation. So let's say we had an ONI value that was indicative of El Nino for 1 month. Well, that doesn't tell us we're in an El Nino phase. We want to see that over a longer period, and thus we use these 3-month running averages. If we have an ONI value that is greater than positive 0.5 for a given 3-month period, meaning that the average sea surface temperature anomalies in the Niño 3.4 region for that 3-month period are greater than positive 0.5 degrees Celsius, we would be in a warm phase. And if we have an ONI value less than minus 0.5 or more negative than negative 0.5, we would be in a cool phase or cold phase. And anything in between that 0.5 and 0.5 threshold would be considered a neutral phase. And if we have 5 consecutive 3-month running average periods, so we have 5 of those, January, February, March, April, and so on and so forth. If we have 5 of those in a row in a warm phase, we would be in an El Nino. If we have 5 of those consecutive 3-month periods in this cold phase, we would be in a La Nina. And if we have 5 consecutive months in that positive 0.5 to negative 0.5 range, we would be in a neutral phase. So that is how we use the Oceanic Niño Index to calculate ENSO phase. And for our purposes here, at least to begin with, we're going to use the Oceanic Niño Index to determine our ENSO phase. And you'll notice here from this graph of Oceanic Niño Index going back to 1950 that ENSO occurs in cycles, hence the name El Niño Southern Oscillation. This is effectively an oscillatory wave. We oscillate back and forth between these El Nino and La Nina phases. Now, El Nino phases tend to last several months to about a year, while La Nina phases can last a little bit longer, several months to maybe up to a couple of years. So now that we've gone through a little bit of a crash course on the El Niño Southern Oscillation and how it's measured, let's take a look at the current state of ENSO that we find ourselves in. This is a map of current sea surface temperature anomalies from across the globe. And once again, I want you to focus on that region of the Pacific along the equator. Here's the 0-degree latitude line, and we're focusing on this region right in here. You'll notice we have some fairly weak, cool anomalies across this region. Now, to put this in perspective, this was what we were seeing at this time last year. And you'll notice in this region that we have quite a bit stronger, cool anomalies. Now, this color scale is a little bit different than what we were seeing on that previous map, but the overall idea is that we were seeing a lot stronger cold anomalies there in that equatorial Pacific region than what we were seeing this year. So last year, we were firmly entrenched in a La Nina phase, and we are starting to come out of that phase as these cool anomalies start to weaken a little bit. And you can see some more evidence of that using our Niño 3.4 index graph here. Now, this is not Oceanic Niño Index like we talked about just a couple minutes ago. This is just simply the average sea surface temperature anomaly across that Niño 3.4 region plotted on a daily basis. And you can see back in December that we were firmly entrenched in that cool phase, but we've now started to see a gradual trend toward a much more neutral phase, and we find ourselves with that Niño 3.4 sea surface temperature anomaly currently at about minus 0.3, which puts us well within that neutral range. And if this continues, as it is expected to, here is the forecast for ENSO from the International Research Institute at Columbia University. A bunch of different climate models go into this, and this is how the forecasts for the El Niño Southern Oscillation going forward are made. And you can see that we start off the year with this weak La Nina in place, But by the middle of spring, we start to see where most of the models are firmly entrenched in that neutral phase. And then by fall, it's likely that we see an El Nino phase start to develop. So during the spring, we should be entrenched in this neutral phase of ENSO. As you see, the sea surface temperatures are trending that way currently as well. Now, we can see as we take a closer look from the Oceanic Nino Index graph that we looked at, that we have actually been in this La Nina phase for quite a while now. The end of last year was actually our third year La Nina, which is quite unusual. La Nina does tend to hang on a little bit longer than the El Nino events, but to see a third-year La Nina is pretty uncommon. And if we take a look at our numerical view here, these are Oceanic Nino Index values plotted. Each 3-month running average is listed from left to right, going back to 1950, and you'll see a lot of blue here, indicating a lot of cold anomalies in that Oceanic Nino Index value, going back all the way to the end of 2020. So toward the end of last year, we were going into our third La Nina year, which is, again, quite unusual. So what impact that will have on the tornado frequency and distribution this upcoming spring is a little in question, whether it will have a big difference or not. But the main thing to know is that we are heading from this La Nina into a more neutral state, as is forecast going into this spring and summer. So what impact might this have on the tornado frequency and distribution this spring across the U.S.? First, let's take a look at some conceptual models of the atmospheric conditions typically associated with each ENSO phase during the winter. Now, these do extend into spring a little bit, although with slightly less significance or clarity. But generally, the pattern is going to be somewhat similar to what we see with each ENSO phase during the winter, which we are showing here. So the top panel is our El Nino phase, and our bottom is the La Nina. So you'll notice with the El Nino phase that we tend to have a somewhat lower amplitude, slightly southward shifted but fairly active jet stream. That leads to a wetter than normal southern third of the country. Whereas with our La Nina phase, we tend to have a higher amplitude jet stream that is shifted a little bit farther north. Therefore, we tend to have a drier than normal southern third of the country. However, as we go into spring, you can see how this might change. The jet stream tends to dip a little bit farther south in general during the spring months. So that is going to bring more of these waves, these higher amplitude waves, into the U.S. What is the result of that? Well, you get more waves traversing the Rockies. You'll get more frequent lee cyclogenesis, or surface cyclone development on the east side of the Rockies. What does that lead to? Well, that leads to stronger low-level mass response, greater moisture return farther north into regions like the plains and the southeast, even the Midwest, and a stronger low-level jet across the region, more instability, more low-level wind shear. Therefore, La Ninas in spring are generally associated with more active conditions as far as tornadoes and tornado outbreaks go. You can see that with the El Nino phase, with a slightly southward shifted jet stream, you'll have the storm track a little bit farther south, so these waves are not going to make it as into the U.S. They'll take They'll take a more southern track. Therefore, the moisture return with these systems is not going to make it as far north. Therefore, this tends to shut off tornado activity a little bit in typical regions like the plains into the Midwest during El Nino years. Now, the neutral phase is somewhat in the middle of these two, but there has been quite a bit of research done on these phases, including the neutral phase and tornado activity in the U.S. I want to first draw your attention to this paper by Cook et al. 2017, where they looked at the impact of ENSO phase on winter and early spring U.S. tornado outbreaks from 1950 to 2010 to see if there was a linkage between ENSO phase and the tornado outbreak frequency in the early portion of the year. They looked at the period from January through April. Obviously, we're focused on those spring months, March and April. And I want to refer you to their figure 3C and D. You're looking at figure 3C right here. And these show for March and April, respectively, the normalized tornado counts for each ENSO phase within each month in the study period. So essentially what they did was they made a grid east of the Rockies for the entire U.S., totaled up the number of tornadoes within each grid box, and then divided by the number of months where each ENSO phase was present in the study period. So, for example, let's say one grid box here for the El Nino phase, which is on the top left. Let's say we had 10 tornadoes in a given grid box, and let's say we had 20 Marches where El Nino was present in the equatorial Pacific. We would divide 10 by 20, which would be 0.5, and that would be our normalized tornado count for that grid box. Obviously, those are not the real numbers. I'm just giving you an example of what these figures are showing. And they use this normalization technique because neutral months appeared far more often in the study period than El Nino and La Nina months. So that is a well-known facet of the El Niño Southern Oscillation during the spring. Oftentimes, the spring months will see the El Nino transition from one phase to another and will be in these neutral phases. So they appeared far more often in the study. And if we were to leave the tornado counts as is, the neutral months would show a far higher frequency of tornadoes than the El Nino and La Nina months, simply because there were so many more neutral months than La Nina and El Nino months. So they had to normalize it so that we were looking at similar numbers among these ENSO phases. So again, Figure 3C, these are for all of the months of March in the study period, 1950 to 2010. El Nino is on the top left, La Nina on the top right, and neutral on the bottom left. And you can pretty clearly see a disparity between El Nino and both La Nina and neutral Marches. El Nino tends to have a somewhat suppressed frequency of tornadoes across pretty much the entire study area, while La Nina definitely has a bullseye down there in the southeast. But take a look at the neutral months. We definitely have somewhat of an enhanced tornado frequency across parts of Oklahoma into Missouri and Arkansas, with a more general increase in frequency denoted by the yellow contour here down into North Texas into the southeast. So the neutral months of March do tend to have somewhat increased frequency of tornadoes, especially across that central plains to the sort of Arklatex to Arklamis Mississippi River Delta vicinity. But going to April is where the trends really stick out. Once again, El Nino on the top left, La Nina on the right, top right, neutral on the bottom left. Again, these are for the months of April within the study period. And you can clearly see, once again, El Nino has a very much decreased frequency of tornadoes across the CONUS, with an increase shown in La Nina. But look at the neutral cases. We have a bullseye of enhanced tornado frequency here across the somewhat typical areas that we think of where tornado activity increases during the early spring months. Kansas, Oklahoma, into North Texas, with a bullseye right there in north central Texas. We also see a little bit of an increase during neutral Aprils up here into the Midwest. Places like Illinois may see some slight increases in activity along with our typical tornado alley areas. So this is a little bit a decent piece of evidence supporting a fairly active early portion of the season, March into April, especially for the typical tornado alley areas that get going, that really start to rev up in the early spring months. Now we can take this a step further, and instead of looking at the actual ENSO phase we'll be in during the spring, we can look at the entire ENSO progression throughout those spring months to give us maybe a better prediction of how tornado activity will progress during that spring season. And that's exactly what Lee et al. 2016 did in the paper you see here. They identified 4 different dominant ENSO progressions that tend to most efficiently modulate tornado outbreak frequency in the U.S. in a given spring. The first one was a persistent El Nino, in which an El Nino is present throughout the entirety of spring. An early terminating El Nino, where you start off with an El Nino that transitions to La Nina. A resurgent La Nina, which is otherwise known as a second-year La Nina. So you have a La Nina in the prior year that continues into the second year. And then this final one is called transitioning La Nina, where we start off with a La Nina transitioning to an El Nino phase by the end of spring. Well, that sounds awfully familiar. That's what we discussed as what we're going to be seeing over the next several months as we go into spring. So this transitioning La Nina really fits our current situation fairly well. Here is their supplementary figure 5 that shows the typical sea surface temperature anomalies and tornado outbreak probabilities for a transitioning La Nina setup. So on the left, you'll see the sea surface temperature anomalies, and they look pretty similar to what we have going on right now. Fairly decent cool anomalies across the equatorial Pacific in the late winter, early spring months. Then by middle of spring, April or so, we start to see those anomalies weaken quite a bit toward closer to a neutral state. And then by late spring, May or so, we start to see that neutral state take shape, maybe even into slightly a warmer phase of ENSO. What impact does that have on tornado outbreak probabilities? Well, let's zoom in here on these maps at the right. So the top one here is March, April, and May on the bottom. Wherever there's shading, there is an enhanced probability for tornado outbreaks in that region, and any grid box that has a black dot in it, let me zoom in for you so you can see that, any grid box with a black dot in it is statistically significant at the 10% confidence level. Just means we have higher confidence in the results in those regions. But in general, any region where there's shading, the orange and red shading, is where there is a heightened potential for tornado outbreaks across that region. So we'll start off here with March. Our favorite areas look to be anywhere from eastern Oklahoma up into the Midwest, with some semblance of heightened probabilities there in the southeast. But when we move on toward April, that's when this linkage really starts to shine, and you'll see very strong enhanced probabilities there in, once again, your classic areas that are favored for severe weather in the spring: Kansas, Oklahoma, into northwest Texas. So in the past several years, we've had a relative drought, especially in Oklahoma, as far as tornadoes go. Haven't really had a classic Oklahoma outbreak since maybe back even into 2012, April of 2012. Of course, we had those couple weeks in 2013, but since then, it's been quite quiet here in the central to southern plains, specifically Oklahoma. This research suggests that we may see, given our background ENSO pattern, we may see somewhat of a return to a more classic, at least first half of the season, as far as enhanced outbreak potential or tornado potential in those more favored areas of the plains, that central to southern plains corridor, Kansas, Oklahoma, into Texas, focusing on April, where the linkage seems to be strongest. As you go into May, the linkage not quite as strong. We do see maybe a couple of enhanced areas there in the central plains, the Kansas-Nebraska border region, some areas down there in Texas, but for sure the linkage is definitely strongest in the first half of spring, March into April. So all in all, the Cook et al. And Lee et al. Research here and our background ENSO progression does suggest that we may see an active, perhaps above average, first half of the season, March into April. The linkage, again, decreases a little bit as we go further into spring, and we'll talk about that a little bit more in a second, but it does appear that we are in for potentially a fairly active continuation of the fairly active pattern we've been having into these first couple months of spring. Let's look at some other research now. This is a paper by Lepore et al. 2017, looking at ENSO during the March and May period for U.S. tornado and hail activity. And we'll scroll down to their figure 2 here, particularly 2E. This shows the probability of below or above average severe convective storm activity for the United States during a weak La Nina phase. And you could consider this early portion of the spring to be a weak La Nina. As we said, we're transitioning from that La Nina into that neutral and eventually El Nino phase. But at least for this early portion, we're still hanging on to maybe some weak semblance of La Nina. And you'll notice here that the green colors are above average probabilities for severe convective storms. As we know, those can produce tornadoes and large hail. And you'll see some bullseyes here, some enhanced areas there in those same areas we were talking about, Oklahoma down into Texas. And really, most of the United States does feature an enhancement in the probabilities for severe convective storms, with the greatest potential down there in the plains regions, maybe somewhat in the Midwest as well. But it is a well-known, well-researched fact that La Nina does tend to enhance severe convective storm potential across the U.S., and in turn, tornado potential in those areas that we discussed. And one more paper here from Mays et al. 2008. They focus on the El Niño Southern Oscillation's effect on the synoptic scale convective environment over the north-central United States. And they discuss the characteristics during a dissipating La Nina, or as they call it, the La Nina going out phase. So that would mean a La Nina episode that is weakening with time, which is basically what we're seeing here in our current situation. They do note that the synoptic scale features during a dissipating La Nina do support convective activity, particularly in the high plains where enhanced moisture and low pressure anomalies best coincide. So the high plains, that would be your central and northern high plains, especially Kansas, Colorado, Wyoming, Nebraska, could see an enhancement in convective potential, including the potential for tornadoes up in that region during the dissipating La Nina to neutral phase, as well as the northern plains, which is also a favorable region given sometimes enhanced northwesterly flow, which can be a favorable setup for severe convective storms. Not necessarily tornadoes, although when you have severe convective storms, you always have a chance for tornadoes, even in northwest flow environments, and enhanced baroclinicity. So lots of those strong low pressure systems getting their act together in the northern plains. That could also be a favored region in this sort of dissipating La Nina phase for enhanced convective activity, which could lead to enhanced tornado potential across the high plains. Now, you may have noticed that a lot of the research we've looked at, and a lot of what we talked about in this video so far, has focused on those early spring months, especially March and April. Well, that's because the linkage between ENSO phase and tornado frequency and distribution across the U.S. weakens significantly as we go later on into the spring, i.e. May and June. Let's take a look at some of these charts from the Storm Prediction Center. We'll take a look at January, February here just as an example. These charts may look a little bit confusing at first, but we'll walk you through how these work here now. So on the x-axis is our 2-month period, in this case January through February. We start over here on the left side with January 1st and we go all the way through to the end of February over here on the right. So time increases as you go to the right on the x-axis. And each of these rows represents the running total or accumulating daily sum of tornadoes over this time period for a given year. And the strongest El Nino years are ranked at the top, and we go all the way down through the strongest La Nina years down here at the bottom. So these are the strongest El Nino years at the top. Then we lessen a little bit more. These here are more moderate years, and then we finish off with stronger La Nina years down here at the bottom. And so the brighter colors indicate greater accumulating daily tornado sums for a given year, and the darker colors are lesser sums. And we want to pay attention to this R-squared value here. This is called variance, and this, in our case, tells us how much of this variance in accumulating daily tornado sums comes from ENSO phase. And this 12% R-squared value here is a relatively high number. And that tells us that for these early months, January, February here in this example, that ENSO phase and tornado frequency in the U.S. is fairly strongly related. And you can see here just visually that most of the higher accumulating sums here are located at the bottom, which are our strongest La Nina years. So the ENSO phase is much more linked to tornado frequency across the U.S. in these early months, February through March. Here, R-squared variance value of 6%. That's still relatively high. And for March through April, our R-squared value is 10%. Still, you can see some of those highest counts here for, in this case, March through April occur down here again with our strongest La Nina years. So for this early portion of the year, ENSO phase is much more a factor in modulating tornado frequency across the U.S. But as we get into May and June, later in the spring, you can see that the R-squared value drops off significantly. Here we're at 2% for the May through June timeframe, and you can see there's just not much correlation here between the ENSO phase and the tornado frequency in the U.S., or the accumulating sum of tornadoes across the U.S. in each of these years. So that gives us a little bit less clarity later on into the spring. As we've talked about before, it's looking like the possibility for a fairly active march into April is fairly enhanced, but we just don't know a lot. But just by looking at ENSO phase and these this particular climate teleconnection later on in the spring, we're going to have to look at some other factors to make that determination about tornado frequency and distribution in May and June. But to sum things up for now, it does look like we may see a fairly active early half of the season, March into April, from our work that we looked at with particularly this Lee et al. Paper, as well as the Cook et al. Paper on tornado counts across the U.S. Now, there are some other indices and climate teleconnections that can also modulate U.S. tornado frequency and distribution during the spring months. This is another paper from Lee et al. This one's from 2013, and they identified an index known as the Trans-Niño Index, or TNI, to be the most correlated with tornado frequency in the U.S. during April and May. All the Trans-Niño Index is subtracting the sea surface temperature anomalies in the Niño 1.2 region minus those in the Niño 4 region, with some normalization techniques applied. And just for a refresher, that the Niño 1.2 region is that one right off the South American coast, and that Niño 4 region is that westernmost one in the equatorial Pacific. So they found that the TNI was most correlated with the tornado frequency in the U.S. during April and May. And if we take a look at their figures 5 and 6, particularly figure 6 here on the right, they've plotted significant tornadoes, F3, F4, and F5s, for 10 positive TNI years here in A, 10 neutral TNI years in B, and 10 negative TNI years down here in C. And you'll notice here very clearly, and let me zoom in on these charts here, when you have a positive Trans-Niño index, you have a very stark increase in all these significant tornado categories across the United States versus the neutral and negative Trans-Niño years. And the synoptic pattern that is associated with positive Trans-Niño years is shown here on the right. We tend to have lowered geopotential heights at 500 millibars here across the western half of the country, placing that central and southeastern portion and midwestern portion of the country generally in that favorable exit region from any troughs that make their way into the U.S. We have increased low-level moisture flux or transport across that region, and we also have stronger low-level wind shear across that southern portion of the country. So positive Trans-Niño index years tend to have a higher frequency of tornadoes across the United States. Here is a graph of Trans-Niño index dating back from 2000 all the way to present day here in 2023. You'll notice it fluctuates quite a bit. You'll notice that it does somewhat correlate to some of our stronger years. Just off the top of our heads, 2011 obviously was kind of the banner year for tornadoes across the United States. You'll notice the very positive Trans-Niño index value associated with that year there. 2008 was also a very active year on the plains, very strongly positive Trans-Niño index there. And you'll notice here, present day, we are trending somewhat positive with the Trans-Niño index. How far this goes into the positive is unknown at this point, but it does look like we are on our way into the positive territory with the Trans-Niño index over the coming months. So this could be a piece of evidence in support of potentially a more active tornado season across the U.S. now that the Trans-Niño index is trending positive, based on our research from Lee et al. 2013. Now, these other climate teleconnections can become quite the alphabet soup of abbreviations. I'm sure many of you have heard of the different ones, the MJO, the NAO, the PDO, the AO, etc., etc. And it can become a real jumbled mess. But there's one in particular I want to talk about, and that is the Pacific Decadal Oscillation, or PDO. And the PDO has to do with how sea surface temperature anomalies look in the Pacific Ocean. When you have colder than normal temperatures in the North Pacific and warmer than normal temperatures along the North American coast, you are in the positive phase of the PDO. When the opposite is true for the negative phase, when you have warmer than normal temperatures in the North Pacific and you have colder than normal temperatures along the North American west coast, you are in the negative phase of the PDO. And the negative phase of the PDO is much more favorable for the intrusion of Rossby waves into the United States. As we know, that can increase severe weather chances for places like the plains, the southeast, etc., etc. So in the negative PDO phase, we are at a higher likelihood of seeing severe weather in the U.S. Let's go back to our graph of the PDO, going back all the way to 1854, and you can see we've been entrenched in a very strong PDO for quite some time now, dating all the way back to late 2019. That was the last time we saw a PDO value in the positive. Since then, it's been in the negative, sometimes deeply in the negative. In fact, last month, February 2023, at a minus 1.67. So we have been entrenched in a very negative PDO for quite a while. Hence the frequent intrusion of these troughs, these high amplitude troughs into the region, and the frequency of severe weather, especially over the past several months. Now that looks to continue into the upcoming months. As long as this PDO stays negative, we should see a fairly active Rossby wave train making its way into North America, particularly the U.S., and that can heighten the chances for severe weather and in turn the chances for tornadoes as a whole across the U.S. in the coming months as we go into spring. All right, let's dive into our next modulating factor, and this one is a lot simpler than all the climate teleconnection stuff we just talked about, and that is the sea surface temperatures in the Gulf of Mexico. As we know, the Gulf of Mexico is our moisture source for severe weather events across much of the country, the plains, the southeast, the Midwest. And as you might expect, quite intuitively, when the Gulf of Mexico sea surface temperatures are warmer than average, the severe weather frequency, including that of hail and tornadoes, increases across the southern U.S. When you have cooler than normal temperatures in the Gulf of Mexico, you'll have less severe weather across the southern U.S., particularly in that March through May time period. This paper from Molina et al. 2016 goes into the linkage between the Gulf of Mexico sea surface temperatures and U.S. severe thunderstorm activity, and as we scroll down to their figure 3, we'll see it has to do with instability. Warmer air holds more moisture, and so a warmer than normal Gulf, that air mass that sits right above it and it gets transported inland on the low-level jet in these types of tornado setups, is a lot juicier. It holds more moisture, it's a lot juicier, holds more energy, and is more unstable than if you had a much cooler air mass which can't hold as much storm fuel, if you will. So a warmer than normal Gulf is able to transport a much juicier air mass inland, and therefore when you have a warmer than normal Gulf, you have more energy for storms to use in these severe weather setups. This figure shows the mixed layer Cape anomaly for years where you have a cold Gulf of Mexico here on the left and a warm Gulf of Mexico here on the right. Now, for this paper, they split up the Gulf of Mexico into two different boxes, similar to our ENSO regions there in the equatorial Pacific. I want to just focus on the top boxes here. This is the full Gulf of Mexico, when the full Gulf of Mexico is colder than normal here on the left and warmer than normal here on the right. And you'll see a pretty stark contrast between the mixed layer Cape anomalies in both maps. When you have a cold Gulf of Mexico, you'll see that we have a reduction in the overall mixed layer Cape that's available for these setups to use in the southern U.S. These blue colors are a negative mixed layer Cape anomaly. Whereas on the right, you see a widespread area across the U.S. where mixed layer Cape is greater than normal when you have a warm Gulf of Mexico. So very intuitive stuff right here. When you have a warmer than normal Gulf of Mexico, you have a greater likelihood for severe weather due to an increase in the energy and juiciness of the air mass for storms to work off of in these setups. So let's take a look at our current state of the Gulf of Mexico, and you can see right off the bat a lot of yellows, oranges, and reds here across the entirety of the Gulf. That means almost the entire Gulf is running well above average as far as sea surface temperatures go. So we have definitely a warmer than average Gulf of Mexico, and that has partly been the reason that has added to the severity of these off-season, these wintertime or cool season severe weather setups. You have the forcing from things like the Pacific Decadal Oscillation, bringing lots of waves into the U.S., but we've had a very juicy air mass to work with because we haven't had a lot of cold air intrusions into the Gulf. Oftentimes during the winter months, you'll see these very strong cold air intrusions, these cold fronts, push the moisture off well into the Gulf, push cold air well down into the Gulf, and you'll see sea surface temperatures decrease as a result. Well, that hasn't been the case this spring, and it's unlikely to be the case going forward. We're not likely to have a lot of cold air intrusions into the Gulf over the next few months. So this Gulf should stay boiling for our spring severe weather season. Therefore, this is another factor that may increase the likelihood and increase the frequency for tornadoes across, especially the southern half of the U.S., but because we have a warmer than normal Gulf, we may see that moisture surge even farther inland, places like the Midwest, Illinois, Indiana, up in the Great Lakes region even, for our severe weather setups moving forward because we have such a warm Gulf. So that is a factor that is definitely leaning toward an above average year for tornado frequency across the U.S. The last major modulating factor we can look into is drought in the elevated mixed layer source region. And that includes the Rocky Mountains all the way down to New Mexico, West Texas, and Western Mexico. And we've talked about the elevated mixed layer, or EML, ad nauseum on the channel here. The EML is simply that layer of warm, dry, well-mixed air, steep lapse rates that emanates at and just above the surface in that EML source region. And on those mid-level westerly or southwesterly winds, gets transported out to the east atop that low-level moist layer, and it can help allow instability to build by prohibiting storm formation through much of the day and allowing maximum instability to be realized once that cap finally does erode. Now, what does drought have to do with it? Well, if you have enhanced drought in the EML source region, your elevated mix layer is going to be much warmer, much drier, much stronger, and may actually work to prohibit storm formation altogether in given plains setups. So you want to see that drought as minimal as possible in that EML source region so that the cap is not too strong for setups out to the east. Now, the caveat to that is sometimes if you have a stronger EML and you're talking about setups in the southeast, that may actually work in the favor of southeast setups. Oftentimes, southeast setups don't have any EML at all to deal with, so you have just a lot of storms going up at once, a bit of a mess as far as storm mode goes. But if you have a strong EML in place, that can help cap that air mass to prohibit storm formation through much of the day. We saw it on April 27th, 2011. The early morning soundings on that day had a pretty stout capping inversion in place, and that was due to a very strong EML out to the west. So it can work somewhat both ways. On the plains, if you have too strong of an EML due to a little bit of an enhanced drought in the EML source region, you can have a cap that is too strong to erode fully, and you can see a decrease in the overall frequency of severe storms and, in turn, tornadoes. Whereas out to the southeast, that may work in the opposite manner, where you can actually have a more potent setup because of a stronger EML in place. So let's take a look at what we're experiencing right now as far as drought goes across the U.S. This is the latest U.S. drought monitor map from the University of Nebraska at Lincoln, and the darker colors indicate the most intense drought. So the oranges, reds, and dark reds indicate severe to exceptional drought, while areas in white are experiencing no drought at all. And right off the bat, you'll notice that we do see some fairly strong signals for drought across the central plains there. Kansas struggling mightily with drought at the current time, as well as up into northeast Nebraska, down into central Texas as well. But our EML source region, we're taking a look here at the Rocky Mountains down into New Mexico and West Texas. You'll notice we're not doing too bad as far as drought goes. We're seeing, I would consider this moderate drought. We see a lot of yellows and those tan colors. That indicates abnormally dry conditions to moderate drought across the region. Some darker colors in there, some more severe drought in there, but for the most part, I would consider this as moderate drought. We can go down as well into Mexico. This was a little bit older, but this is the most current drought monitor map for Mexico. Arizona's right here, New Mexico's right here, and this would be Texas. So most of Mexico dealing with some abnormally dry conditions to moderate or severe drought. So not doing too bad in Mexico as well, but there is definitely some drought that is present across the EML source region. Now this is a pretty decent indicator for and pretty decent linkage between this and tornado frequency in the plains. Just looking at a few examples, this was last year's drought monitor map. For those of you chasers out there who were chasing last year, you remember that especially May was pretty quiet as far as tornado activity goes, and we did see quite a bit of drought in that EML source region, especially in southern areas there, New Mexico into West Texas. Very strong drought in place last year. Another year that was quiet as far as tornadoes go, that was 2013. Even though we had our 2-week stretch there in May that was pretty intense, we did see quite a bit of drought again in that EML source region into the high plains. And then for an active year, 2008 was very active as far as tornadoes go in the spring, and you see minimal drought there in the EML source region on the higher terrain out west. So this is a pretty good linkage between the strength of the drought in the EML source region and tornado frequency in the areas to the east during the spring. And here's our forecast for the upcoming spring months. So this is the 3-month outlook for March through the end of May 2023. And areas in brown and yellow are where drought is expected to persist and drought development is likely. And you see that all that EML source region, the Rocky Mountain areas, the higher terrain out to the west, eastern New Mexico down into West Texas, drought is expected to persist throughout the region. And you have to keep in mind that these drought monitor maps are current. This was taken at the end of February, released on March 2nd. So this can change throughout the year. We could see drought worsen a little bit in this region. That could have some impacts later on down the road on the EML strength. But for now, we're seeing moderate drought that is likely to persist through the spring. Here is the Climate Prediction Center seasonal temperature outlook for March, April, and May. You see we have the forecast for above average temperatures and below average precipitation across this region. So some interesting signs here. We may see that drought continue to worsen across especially the southern portions of the EML source region, New Mexico, West Texas. We'll have to keep an eye on that. If we do see a significant strengthening of that drought in the southwest region, then we may have some issues later on down the road for especially April into May and June for these areas out to the east, the southern plains, into the central plains and Midwest. So we'll have to watch that for sure. Right now we're seeing just moderate drought, which is not terrible. If we saw quite a bit of red and dark red throughout this region, I'd be a lot more concerned. As we saw, for example, last year, I would be a lot more concerned with this particular situation as far as the EML goes than I am with this situation right now. And one caveat to this is that this drought factor is not the most important factor. The way that you erode the cap is to have, number one, strong low-level warm moist advection to warm and moisten that low-level layer beneath that capping inversion. And number two, to have a strong trough move-in that allows this capping inversion to be lifted and cooled. And that's how you erode the cap. And we've already established that our Gulf of Mexico, which is our moisture source, is pretty much boiling right now. We have a very warm, moist Gulf of Mexico that should provide a very steady source for strong moisture advection in the low levels this season. So that's not an issue. And we already have said that, especially through the early half of the season, March and April, we should have the continuance of a lot of strong troughs moving into the region. So that will allow, even if the drought in this region does worsen a little bit over the coming months, I don't think we're going to see too many issues as far as drought goes and too strong of an EML goes, because we're going to have continued strong troughing and strong low-level warm moist advection. I think that will be able to overcome any capping issues that we might have going forward. But for now, it looks like we do have some drought to deal with, and we'll have to monitor this situation over the next few months to see if this does worsen, as it could have some impacts on the EML, although I'm not super concerned with this particular look at the moment. All right, let's get into the part that you've all been waiting for. Let's go over some analogs. Those years in the past that had similar background conditions to what we're expected to see both now and going forward through the spring, regarding ENSO phase progression, drought conditions in the EML source region, and Gulf of Mexico sea surface temperatures. Now, this was somewhat of a subjective exercise. I had to go through and use my own judgment to pick out the years that looked most similar to our current situation. And one note, I cut off my analog search at 1950, simply because if you go back any farther than that, the data just gets really sparse. So I cut off my search and used the range from 1950 to the present day. So I first went in and looked at this chart of the Oceanic Niño Index to determine ENSO phase. And I wanted to look for those years that had the transitioning La Niña as described by Lee et al. 2016, that it was occurring during spring, and specifically those years that had a multi-year La Niña preceding it. As we talked about earlier, we were in our third year of the La Niña phase, and now we're finally transitioning out of it. So I wanted to look especially for those years that had a multi-year La Niña preceding the transition. So I went in and did that, and these were the years that I came up with. All of these years had a transitioning La Niña occurring during the spring months. Now, this is not only those years that had a multi-year La Niña preceding the transition. These are all the transitioning La Niña years that I found in the database since 1950. I then went in, and for each of these years, I went ahead and looked at the drought conditions in the EML source region. Now, those drought monitor maps we showed earlier only go back to 2000, but there is an archive for something called the Palmer Drought Severity Index going back to 1950. The Palmer Drought Severity Index is a little bit different from those drought monitor maps. It basically takes a look and looks at the areas for prolonged dryness or wetness. So these Palmer index values don't change very frequently, very much on a week-to-week basis. This is more for long-term significant drought. So this is actually our current Drought Severity Index, Palmer Drought Severity Index map. The areas in darker orange are those that have seen extreme prolonged drought, and the green areas are all that have had an unusually moist spell. Now you'll see for our EML source region out here, similar to what we saw on the drought monitor map, we have some moderate to severe drought out here across South Texas into the EML source region, West Texas, eastern New Mexico, up into southeast Colorado, a little bit up into the central plains as well. So I went ahead and compared this current map that we're seeing to the historical Palmer Drought Severity Index map going all the way back to 1950 for those years that we mentioned. And I looked for years where we had that very similar looking drought conditions in especially that southern portion of the EML source region. To narrow things down even further, I went and looked into the sea surface temperature anomaly archives for the Gulf of Mexico. And unfortunately, those archives only go back to the mid-80s. Before that, we don't have any sea surface temperature archive data that I could find. So we do have a couple analogs that will be prior to the cutoff for the sea surface temperature anomaly chart archives. But again, it's the main drivers for these analogs are going to be the climate teleconnections as well as the drought in the EML source region. So, and then once I narrowed down the list of analogs to just a few, I went into the wonderful Tornado Archive website and plotted the tornadoes for March through June of those years, as well as the individual months March, April, May, and June for each of those analog years to give us an idea of what those years saw as far as tornado frequency and distribution. And these are the analogs that I came up with. These are color-coded by how good of a match they are to our current situation. The ones in pink are the best matches, the ones in red are the next best, and the ones in orange are good but still slightly weaker, while those that are not labeled had very similar ENSO progressions but very poor matches to the drought and Gulf of Mexico conditions. So our best analogs here are 1976 and 2002. 1976 was a multi-year La Nina that was transitioning to an El Nino during the spring of 1976. So a very good match to our current conditions as far as the ENSO progression goes. If we look at our Palmer Drought Severity Index map from March of 1976, so going into spring, you do see we have some moderate drought here across the EML source region, up from eastern New Mexico into southeast Colorado, southwest Kansas, the Oklahoma panhandles. So some moderate drought, a decent match to what we're seeing with our drought conditions so far. And just a note on these Palmer Drought Severity Index maps, the color scale is a little bit different than what we saw with our present day map, but you can still see the overall distribution of the drought fairly well. Moderate drought in the EML source region, fairly good match to what we're seeing in our present day situation. So here is our tornado map from March through June 1976. A couple of hotspots you see right away. We see a very nice concentration of tornadoes down here in the southern portion of the country, especially Texas into the southeast. We also see a little bit of an increase, a little bit of a hotspot there in the Midwest. Places like Iowa, Illinois, Indiana, up into the Great Lakes had a nice hotspot for tornadoes. Let's go month by month now. This is March 1976. Hotspot down there in the southeast, places like Louisiana, Mississippi, Alabama. And the Midwest activity occurred early in the season in March here across Illinois up into Michigan. We move on to April. Fairly quiet overall, but we do see a tendency toward the favored locations for severe weather from the Kansas-Nebraska border down through western Kansas, western Oklahoma, with a hotspot down in north-central Texas. We move into May. May, fairly quiet as well. We had a little bit of activity up here on the central to northern high plains, Colorado, Wyoming, and a continued focus on much of Texas for May, but overall fairly quiet. And then we go into June, and fairly sporadic activity with a little bit of a hotspot up here in the northern plains, North Dakota, as well as some activity in the Midwest, Iowa, southern Minnesota, into Wisconsin as well. 2002 was similar. We were coming out of a multi-year La Nina into a neutral or ENSO phase. There was a little bit of a quirk here, and we started to come out of the La Nina phase in 2001, but we rebounded slightly, and those sea surface temperatures in the equatorial Pacific started to cool a little bit again before finally we rebounded and went back into our transitioning La Nina progression. So this was slightly weird. I wasn't sure whether or not to pick 2001 or 2002. I ended up going with 2002 since that is when the transition to a neutral or El Nino phase started to occur. But overall, fairly similar transitioning La Nina progression. let's look at our drought severity index. Similar looking drought. The West was struggling quite a bit with drought in general. We did have some moderate drought here across far west Texas into the Oklahoma Panhandle, some of the higher terrain out here into New Mexico. So somewhat similar as far as drought goes. Here is our drought monitor map since we are post 2000. We do see at the start of March some moderate drought across this region. So a fairly decent match to what we're seeing right now. Sea surface temperatures in the Gulf of Mexico. We start with a warm blob here in early March with some areas of cooler than normal temperatures on either side. But by April and into May, we warmed considerably. And by May, we had the entire Gulf of Mexico warmer than average, similar to what we're seeing right now. So what about our tornado counts? Here's 2002's March through June map. Not a whole lot of activity in general, not a ton of strong activity. You see a few longer tracks here, even one out there on the East Coast. But mostly short track, weaker tornadoes, but we did have a preponderance of those in the typical areas for severe weather. Kansas down to Oklahoma into Texas, with also somewhat of a highlight here in the Midwest to Ohio River Valley. So that is interesting that both 1976 and 2002, what I've deemed to be our best analogs, have some activity in the Ohio River Valley to Midwest region. Let's go month by month now. March, very quiet March across the region, only really focusing on Texas there with some tornado activity elsewhere. Very, very quiet March. April, somewhat similar, fairly quiet April, although that is when the preponderance of our Midwest to Ohio River Valley activity occurred. We did have some stronger stuff down in Oklahoma to Texas, but very sporadic by nature. May was fairly active. Again, not a lot of strong tornado activity, but we did have quite a few tornado reports here from Kansas, Oklahoma, western Oklahoma into the Texas Panhandle and Texas South Plains. So our favorite areas for severe weather development were hitting there in May, but overall not a lot of strong activity. And then in June, mostly sporadic activity. These next couple analogs were still good, but not quite as strong as the first couple. This first one here, 2018, we started off in a similar La Nina progression, although this was not a multi-year La Nina. This was basically a single-year La Nina transitioning to an El Nino phase. Let's look at our drought map. Once again, the West suffering from a lot of drought. We did have a fairly widespread, moderate drought occurring across the EML source region, Colorado down into New Mexico, West Texas, into northwestern Oklahoma. So we did have moderate drought across the region. Here's our drought monitor map from there. Fairly close match to what we're seeing right now. Enhanced drought up here into southwest Kansas, northwest Oklahoma, with some lessening down into eastern New Mexico, west Texas. Fairly similar to what we're seeing right now. Sea surface temperatures in March started off very warm across the entire Gulf. Very warm temperatures there in March. And then by April and May, we started to cool off a little bit. Here's April, here's May. Lots of cool anomalies across the Gulf, surprisingly enough, going into May. And if you were chasing, if you're a storm chaser and you've chased for the past several years, you remember 2018. This was a fairly dismal year for storm chasing, especially into the early spring months into May. And this perhaps could have explained why we saw some cooling here in the Gulf of Mexico come May 2018. But here is the tornado map for March through June. Not a lot of activity, fairly sporadic, not really one location that seems to have gotten hit or gotten impacted more than another location, maybe down here into the southeast early on. Let's go month by month. Here's March, pretty dismal March across the plains, mostly just a few different events in the southeast. There was some very large hail and some tornadoes here across Alabama around the middle of March 2018. April, pretty much the same, extremely dismal across the plains. Really nothing from Texas all the way northward. All the activity was confined to Louisiana, Arkansas, some sporadic activity in the Midwest as well. So we are seeing some signal in these analogs for the Midwest being somewhat active, especially early in the season in these analog years. May, sporadic activity, not really one place that jumps out. Very quiet May as far as tornadoes go. There was the couple of days on May 1st and 2nd, a couple tornadoes up in Kansas and then down in Oklahoma. And then late month, we had a few tornadoes up here from northeast Colorado down into southwest Kansas. But overall, not too much activity in May. And June, very sporadic activity as well. So 2018, a fairly dismal year for tornadoes across the plains, especially, and that is an interesting facet to note as we go through these analogs. 2009, once again, moving from a La Nina to a neutral or El Nino phase during the spring. Similar to 2002, we started to come out of our La Nina phase, but then once again cooled those sea surface temperatures in the equatorial Pacific before finally rebounding and transitioning in the spring of 2009. Here's our palmar drought severity index for March of 2009. Still fairly moderate drought across the southern portions of the EML source region as well as up into Colorado. Little bit stronger drought across much of Texas here with very strong moisture up in the northern to central plains, which was a little bit different from what we're seeing currently. Here's our drought monitor map for March of 2009. We do see that strengthening drought there in South Texas, with maybe a little bit less drought than what we're seeing right now across the EML source region, but still some drought in place across there. Sea surface temperatures in the Gulf, not super similar to our current situation. We did have quite a bit of warming in the Gulf, but we did have some cool pockets as well. We went into April, and by May, we were mostly just above average there across most of the Gulf with a little bit of a cool patch there in the eastern Gulf of Mexico. Now, tornado activity was fairly active in 2009. This was not considered a great storm chasing year. There were not a lot of really great storm chasing events, but there were a lot of tornadoes. We'll go month by month here. March of 2009, not a ton of activity. We do see, once again, the Midwest lighting up a little bit there in the early season, as well as our typical southeast severe weather events, as well as some sporadic activity in the plains. We move on to April, and quite a bit of an active April here. Not really one particular spot seeing the bulk of the activity. Some stronger stuff down here in the Arklatex region, as well as some of our typical areas, Texas South Plains up into western Oklahoma, into Kansas there as well. And then May of 2009, very sporadic activity as well. We had a strong event in Missouri in May of 2009. Continued activity into the southeast in May, which is somewhat unusual, but mostly sporadic activity. And then June, we see a fairly active month with the Central Plains, Kansas into Nebraska, and the High Plains, Colorado and Wyoming. This was a very prolific year for the central to northern High Plains, as well as places like South Dakota into Minnesota with some activity there. These last couple analogs were not quite as good of a match as the first few, either in terms of the ENSO progression not being exactly right or the drought not being exactly similar to what we're seeing right now. And the first of these is going to be 2012. 2012, we were coming out of a multi-year La Nina. However, we didn't really fully go into an El Nino phase as is expected later this year in 2023. We really dipped into the neutral for a few months and then went right back into a cool phase for a few months before a strong El Nino in the 2015 timeframe. So not a perfect match as far as the ENSO pattern goes, but we were coming out of we were transitioning out of a La Nina phase into a neutral phase, so I did include it in our analogs here. Drought Palmer Drought Severity Index, we had quite a bit more drought than what we're seeing right now across the EML source region. We were in extreme drought across this region. It's Colorado down into eastern New Mexico, West Texas. Here's our drought monitor map. We were exceptional drought across this area, so quite a bit more drought than what we're seeing this year back in 2012. Sea surface temperatures, though, fairly similar. We were warm throughout much of the Gulf throughout the entire spring months, especially April there. You see the Gulf very warm, very much warmer than average there. A lot of tornadoes in 2012. There were a few big outbreak days that added to this tornado total. This is our March through June map. Here's March. Again, lots of activity here along the Ohio River into the Midwest, along with our typical southeast activity. So very interesting that most of these analogs do have increased activity early in the season, March and April, up in the Midwest to Ohio River Valley region. Something to really keep in mind as we go forward. April, couple of big days added to this. We had, of course, our April 14th, 2012 outbreak across Oklahoma and Kansas with multiple significant tornadoes there. And we also had a day to start off April 3rd, 2012, down here in the Dallas-Fort Worth Metroplex that had multiple tornadoes. Two big days in April that added significantly to the tornado count for April. But you can see, once again, that our favorite areas, Kansas down into Oklahoma and Texas, are where the tornado activity occurred mostly during the month of April, which is what we were thinking based on the research from Lee et al. 2016, etc. As we go into May quieted down quite a bit, just sporadic activity, not really a hotspot anywhere. Very quiet May, very similar to some of these other analogs that as we go further into spring, we may start to quiet down a little bit after an active early portion. And then June, not really much to speak of, your typical high plains activity there, a little bit up here in the Dakotas into Minnesota, but not a whole lot in the latter half of spring relative to the first couple months, March and April. And finally, 1965. This one is a little bit anomalous as far as tornado count goes compared to the other analogs. Similar transitioning La Nina pattern, although this one time we were in a fairly weak La Nina for a shorter period of time before transitioning into the neutral or El Nino phase in the spring. Drought monitor, drought severity index map, fairly similar. More drought here maybe in the central to northern plains, but our EML source region seeing a little bit of moderate to severe drought, similar to what we have going on now. Lots of strong tornadoes. 1965 was well known for being an active year, especially for strong to significant tornadoes. You see a lot of those red tracks there. Lots of significant tornadoes in 1965. Let's go month by month. March, strong tornado there in northern Oklahoma into southern Kansas. Not a whole lot of activity early on in March, but April, big time Midwest outbreak here. Once again, this was our Palm Sunday outbreak, made up a lot of this, April 11th, 1965. Lots of long track tornadoes in that, as well as our southern plains, Oklahoma and North Texas had was highlighted there in this activity for April. May of 1965 was, unlike the other cases that we've looked at, extremely active, especially for strong tornadoes up here in the central plains, Nebraska. Several strong tornadoes up there in Nebraska into South Dakota, but lots of activity on the plains in 1965, which is anomalous compared to the other analogs we've looked at. Same with June. June stayed fairly active. We did have quite a bit of activity still here in the southern plains, Texas Panhandle up there, as well as our typical high plains activity there in Colorado and Wyoming, as well as a cluster up here in southeast South Dakota and some in North Dakota as well. So what does all this mean for tornado frequency and distribution in the U.S. this spring? We've done all this research, we've looked at all these analogs, all for me to tell you that it's hard to say. Tornadoes are really fine scale features that are dominated and driven by very small scale features themselves, fronts, boundaries, etc. And we just can't predict those at this time scale. There are also other teleconnections that we use, such as the Madden-Julian Oscillation, or MJO, the Arctic Oscillation, or the AO, that change on much smaller timescales than the teleconnections we looked at here in this video, ENSO, the PDO, etc. So it's pretty hard to say at this point. But we do have some things that are going for us. Our pros in this instance, our climate teleconnections look pretty favorable for an active season, at least an active early portion of the season. Research from Lee et al. 2016 and others shows that we may see a fairly active early portion of the season with a return to our more traditional tornado locales, the central to southern plains. We also have a fairly warm Gulf of Mexico. Temperatures in the Gulf are running well above average at this point, and that's likely to continue through the spring, as we're not likely to have significant cold intrusions into the Gulf that would cool those sea surface temperatures. So we have lots of juicy, unstable air ready to be pulled northward into the U.S. for an active season. On the other side of things, our drought. We're going to have to monitor how that progresses through the spring. Again, we have some moderate to some, maybe some slightly severe drought across the EML source region at this point. If we see a significant increase in that drought over the coming months, we may start to talk about some elevated mixed layer issues, some capping concerns with setups. But I do think, given these other factors that are favorable, lots of factors pointing to ample troughiness moving into the country, as well as a warm, unstable Gulf of Mexico, may help to negate the potential impacts from a strong EML. We also have climatology. A lot of our analogs didn't look all that great, especially the later into the season you go. They really seem to focus on that early season, March and April, for our active tornado, the most active portion of the season for tornadoes, whereas we started to get into the later months, not quite as good in some of our analogs, with the exception of a couple, 1965 being one that had an active later half of the season. But that's just going to have to be something we're going to have to wait and see on. But we do have some conflicting signs here. What do I think is going to happen? I think for the remainder of March, we'll see a fairly normal period with storm systems confined to the southern portion of the country. Texas into the Arklatex, Arklamis region into the southeast. I think that's where our focus is going to remain through the end of March. Now, April is a different story. If you're planning your chasecation now, I would highly suggest you do it in April this year. I think April is going to be really active, perhaps quite a bit above average. We are seeing some signs in some climate teleconnections, the MJO, for example, as well as our favorable ENSO pattern, etc., that we may see a fairly active April. And I think, again, we'll see a return to our more favored locales for tornadoes on the plains. Your central and southern plains locations like Kansas, Oklahoma, into Texas. I think that's going to be a favored spot in April, and we very well could see a couple of tornado outbreaks in this early half of the season focused in April. I also think we'll see an active Midwest to Ohio River Valley region. We saw a number of analogs that we looked at, early season analogs showing fairly active Ohio River Valley to Midwest portion of the country. So I would keep an eye on that region as well. I think we'll see an amplified tornado response in that region this early spring. Now, as we go into May and June, as we said, the teleconnections are not quite as strong as they are early in the season. And a lot of our analogs showed that we tend to quiet down in the late spring months. So May and June, I think, may be a little bit quiet. As we've seen the past few years, a hot early season and a return to a more quiet pattern in May and June. Unfortunately, I think that's what's going to happen this late spring. I think we will see perhaps a continuance of tornadoes in our plains regions, Nebraska down through Texas and in the Midwest. But I do think we may see start to quiet down into May and June just a little bit, perhaps a bit below average. June, perhaps a hot spot, maybe up here in the central high plains as well. We may see a return up in Colorado and Wyoming to some pretty good June days, but that's a little bit in question at this forecasting range. So all in all, that adds up to a fairly active first half of the season, fairly below active second half of the season. I think we'll be fairly close to average this tornado season. I think, once again, the front half of the season will be a little bit loaded, March into April especially, and we'll see a little bit of a westward shift compared to the last few years, which may have had a little bit of an eastward bias to the tornado frequency and distribution in the U.S. I think, once again, we'll see a return to those more favored and typical locations for tornado activity on the plains. And then latter half of the season, we might quiet down just a little bit with some nice events sprinkled in there. And keep in mind that we're just talking about tornado frequency and distribution. We're not talking about severe weather as a whole. There's probably going to be a lot of severe weather, a lot of chaseable storm setups. But they may just be more of your hail, your structured type setups. Tornado activity is what we're focusing on here, and I think that's going to quiet down a little bit as we go into the latter half of spring. So, hope you learned something from this video. Once again, it's an interesting exercise that we can at least try to forecast tornado activity in the U.S. at this forecasting range based on a number of different factors. So, hopefully you learned something in this video. This was a fun exercise for me. Hopefully we'll make this an annual thing. Once we get into July or late into the summer, we'll go back and revisit this forecast we made and see how we did based on what happens this spring. So with that, thanks for watching, and we'll see you in the next video.